the heart of nearly every computing device lies a fundamental architectural choice that shapes everything from battery life to processing power. The distinction between x86 and ARM processors represents two fundamentally different philosophies in chip design, each optimized for different priorities and use cases. The x86 architecture traces its lineage back to Intel's 8080 processor, released in 1978. Over decades, it evolved into a complex instruction set computing architecture, commonly known as CISC. This design philosophy emphasizes a rich, extensive instruction set where single instructions can execute complex operations. Intel and AMD have dominated this space, refining and extending the architecture through multiple generations. ARM, which stands for Advanced RISC Machine, emerged from a different design philosophy in the 1980s. Built on reduced instruction set computing principles, ARM processors use simpler, more uniform instructions. Each instruction performs a basic operation, but these operations execute with remarkable efficiency. ARM Holdings licenses this architecture to other manufacturers rather than producing chips themselves, leading to widespread adoption across diverse applications. The architectural differences manifest most clearly in how these processors handle instructions. An x86 processor can execute variable-length instructions, some requiring multiple clock cycles to complete complex operations in a single command. This approach reduces the total number of instructions needed for a task, but increases the complexity of the processor's decode logic and control circuitry. ARM processors, conversely, utilize fixed-length instructions that typically complete in a single clock cycle. This uniformity allows for simpler decode logic and more predictable pipeline behavior. The processor can fetch, decode, and execute instructions in a streamlined manner, though accomplishing the same task might require more individual instructions compared to x86. Power consumption represents one of the most significant practical distinctions. ARM's simplified instruction set and efficient design philosophy result in substantially lower power draw for equivalent computational tasks. This efficiency stems from reduced transistor counts, simpler control logic, and optimized power management capabilities. A typical ARM processor might consume 5 to 10 watts under load, while x86 processors often require 35 to 125 watts or more. This power efficiency explains ARM's dominance in mobile devices, embedded systems, and battery-powered applications. Smartphones, tablets, and Internet of Things devices overwhelmingly rely on ARM processors because extended battery life is paramount. The architecture's scalability allows it to power everything from microcontrollers drawing milliwatts to high-performance server chips. x86 processors traditionally excel in raw computational performance, particularly for single-threaded workloads. Decades of optimization, larger caches, higher clock speeds, and sophisticated branch prediction mechanisms give x86 chips advantages in certain computing scenarios. Desktop computers, workstations, and servers performing intensive computational tasks have historically favored x86 architecture for these reasons. The performance gap, however, has narrowed considerably. Modern ARM processors incorporate advanced features like out-of-order execution, sophisticated branch prediction, and multi-core designs. High-end ARM chips now compete directly with x86 processors in performance benchmarks while maintaining superior power efficiency. This convergence challenges long-held assumptions about the performance ceiling of RISC architectures. Software compatibility has historically favored x86 due to decades of application development for Windows and legacy systems. The vast ecosystem of x86 software created substantial inertia, making it difficult for alternative architectures to gain traction in personal computing. Applications compiled for x86 cannot run natively on ARM without recompilation or emulation, creating a significant barrier to adoption. Recent developments have disrupted this landscape dramatically. Apple's transition to ARM-based Apple Silicon processors for their Mac computers demonstrated that ARM could deliver exceptional performance in traditional computing roles. These chips combine high-performance cores with efficiency cores, achieving remarkable performance per watt ratios. Translation layers like Rosetta 2 allow x86 applications to run on ARM with minimal performance penalties, easing the transition. The server market has also witnessed growing ARM adoption. Cloud providers and data center operators increasingly deploy ARM-based servers for specific workloads, where power efficiency translates directly to operational cost savings. Amazon's Graviton processors, based on ARM architecture, offer compelling price-to-performance ratios for cloud computing tasks. Manufacturing considerations further differentiate these architectures. ARM's licensing model allows chip designers to customize and optimize the architecture for specific applications. Companies can add specialized accelerators, modify cache hierarchies, or integrate custom components while maintaining ARM instruction set compatibility. This flexibility has spawned diverse implementations tailored to particular use cases. x86 processors, manufactured primarily by Intel and AMD, offer less customization but benefit from cutting-edge process technology and manufacturing expertise. These companies invest billions in fabrication facilities and process development, pushing the boundaries of transistor density and clock speeds. The vertical integration of design and manufacturing enables tight optimization between architecture and silicon implementation. Memory architecture and addressing capabilities differ between the platforms as well. Modern x86 processors support complex memory management units with extensive virtual memory capabilities, large address spaces, and sophisticated caching hierarchies. ARM processors have evolved to include similar features, but implementations vary more widely across different ARM chip designs due to the licensing model. The instruction set extensibility presents another distinction. x86 has accumulated numerous extensions over decades, including MMX, SSE, AVX, and others, each adding specialized instructions for specific tasks like vector processing or cryptography. This creates compatibility challenges but allows software to leverage hardware acceleration for particular workloads. ARM similarly includes extensions like Neon for SIMD operations, though the extension landscape is somewhat less fragmented. Looking forward, the boundaries between these architectures continue to blur. ARM processors are scaling up in performance and capability, challenging x86 in traditional strongholds. Meanwhile, x86 designers are incorporating efficiency improvements and heterogeneous computing concepts pioneered in ARM designs. Both architectures are evolving towards similar solutions for modern computing challenges. The choice between x86 and ARM increasingly depends on specific requirements rather than absolute superiority of either architecture. Power-constrained environments, mobile applications, and efficiency-focused deployments favor ARM. Legacy software compatibility, maximum single-thread performance, and certain specialized workloads may still favor x86. As ARM's software ecosystem matures and x86 improves efficiency, the distinction becomes less about capability and more about optimization priorities. Understanding these architectural differences illuminates the engineering trade-offs inherent in processor design. x86's complex instruction set delivers powerful single instructions at the cost of higher power consumption and design complexity. ARM's streamlined approach prioritizes efficiency and scalability, achieving competitive performance through elegant simplicity. Both architectures represent valid solutions to the challenge of general-purpose computing, each excelling in domains aligned with their fundamental design philosophies.